Welcome everyone to Section 3 of the CSWIP 3.1 Welding Inspector course. This section focuses on welding imperfections and materials inspection. It is an important part of the CSWIP 3.1 examination because a competent welding inspector must be able to recognize imperfections, understand how they form, determine their significance, and assess them against the applicable acceptance requirements. Throughout this section, we will work through the 6 classification groups defined by BSEN ISO 6520-1. We will begin with the fundamental difference between an imperfection and a defect. We will then examine cracks, cavities, solid inclusions, lack of fusion and penetration, imperfect shape and dimensions, and miscellaneous imperfections. But our objective is not simply to memorize terminology. As an inspector, you need to understand why an imperfection occurs, where it is likely to occur, how it can be detected, and what can be done to prevent or repair it. We will also consider radiographic appearances because recognizing the characteristic appearance of an indication is an important part of welding inspection and examination preparation. By the end of this section, you should be able to look at a weld imperfection and think like an inspector, identify it, understand its mechanism, assess its significance, and determine which acceptance standard applies. Let's begin with the learning objectives. This slide establishes what you should be able to demonstrate after completing this section. We begin with the terminology. You must clearly understand the difference between an imperfection and a defect, because this distinction is fundamental to welding inspection. You will then learn the 6 major groups of welding imperfections defined by BSEN ISO 6520-1. The first group is cracks. We will examine solidification cracking, hydrogen-induced cracking, and lamellar tearing. The second group is cavities, including gas pores, wormholes, surface porosity and crater pipe. The third group covers solid inclusions such as slag, flux, oxide, and tungsten. The fourth group covers lack of fusion and lack of penetration. These are particularly important because planar imperfections can be structurally significant. We will then examine imperfect shape and dimensions, including undercut, excess weld metal, overlap, misalignment, root concavity and burn-through. Finally, we will consider miscellaneous imperfections such as arc strikes, spatter, torn surfaces and temper color. The final objective is acceptance and repair. Knowing that an imperfection exists is only the first step. You must know how to determine whether it is acceptable according to the specification governing the particular job. So, as we move through the section, keep connecting 3 things: cause, appearance and acceptance. Those 3 concepts will help you both in the examination and in practical inspection work. Before examining individual imperfections, we need to establish 2 terms that are frequently confused: imperfection and defect. An imperfection is simply a deviation from the ideal weld. That does not automatically mean the weld is unacceptable. For example, a weld may contain a small amount of undercut. The presence of undercut makes it an imperfection, but whether it becomes a defect depends on its size and the acceptance requirements applicable to the component. A defect is an unacceptable imperfection. This distinction is extremely important. Think of it this way: identification and acceptance are 2 separate steps. First, identify what is present. Second, measure or evaluate it. Third, compare it with the applicable acceptance criteria. Only then can you make an accept or reject decision. The presentation divides welding imperfections into 6 classification groups. Group 1 is cracks. Group 2 is cavities. Group 3 is solid inclusions. Group 4 is lack of fusion and penetration. Group 5 is imperfect shape and dimensions. And Group 6 is miscellaneous imperfections. For the examination, remember the distinction very clearly. A defect is an unacceptable imperfection. Now that the terminology is established, we can move into the most significant group, cracks. We now begin the first major group, cracks. This section covers several different crack types and mechanisms. You will encounter longitudinal cracks, transverse cracks, radiating cracks, crater cracks and branching cracks. Cracks can also occur in different locations. They may be located in the weld metal, in the heat-affected zone, or in the parent material. From a temperature and mechanism perspective, the presentation identifies hot cracking, including solidification and liquation cracking, precipitation-related cracking, cold or hydrogen-induced cracking, and lamellar tearing. The important point is that the word crack describes the physical discontinuity, but it does not by itself tell you the mechanism. As an inspector, location and orientation provide valuable clues. A crack along the weld centerline suggests a very different mechanism from a crack running parallel to the fusion boundary in the heat-affected zone. Similarly, a stepped crack in rolled plate may point toward lamellar tearing. So don't approach crack identification by memorizing isolated photographs. Instead, ask: where is the crack? What direction is it running? When did it form? And what material or welding condition could have produced it? We will now look more closely at why cracks are considered such a serious imperfection. A crack is a local rupture in the solid state associated with cooling or stress. The reason cracks are treated so seriously is their geometry. Unlike a rounded pore, a crack has a very sharp tip. That sharp geometry produces a severe stress concentration. When the component is subjected to tensile loading, fatigue loading, impact loading or other demanding service conditions, the crack can become a location for further crack propagation. This is why cracks are normally treated much more severely than rounded imperfections such as small pores. The slide also introduces several crack geometries. A longitudinal crack follows the general direction of the weld. A transverse crack crosses the weld direction. A radiating crack develops from a common point. A crater crack forms in the weld crater at the end of a weld run. A branching crack divides into multiple paths. Location is equally important. Cracks may occur in the weld metal, heat-affected zone, or parent metal. Finally, we classify cracks according to their formation mechanism, such as hot cracking, precipitation-related cracking, hydrogen-induced cracking, and lamellar tearing. For the CSWIP examination, one of the most important distinctions is between hot cracks and cold cracks. You should know when they form, where they occur and what conditions promote them. We will begin with hot cracking and solidification cracks. The photograph on this slide shows a solidification crack. The first feature to notice is its location. It occurs in the weld metal, commonly along the centerline of the weld. Solidification cracking develops while the weld metal is changing from liquid to solid. As the molten weld pool cools, solid crystals begin to form. Under certain chemical conditions, low-melting material can remain between the growing grains. At the same time, the weld metal is undergoing thermal contraction. If the remaining liquid film cannot accommodate the contraction strain, it can rupture and produce a crack. The resulting crack may be open to the surface, or it may remain below the surface. On a radiograph, a centerline solidification crack can appear as a dark, irregular linear indication following the weld axis. For inspection purposes, location is therefore a major clue. If you see a centerline indication within the weld metal, especially one associated with a deep and narrow weld profile, solidification cracking should be considered. The next slide explains the metallurgical mechanism and the conditions that make this type of cracking more likely. This slide explains why solidification cracking occurs. The diagram illustrates the relationship between the solidifying weld structure, the remaining liquid film and thermal contraction. High carbon or impurity levels, particularly sulfur and phosphorus, can widen the solidification temperature range. As solidification progresses, sulfur-enriched liquid films can remain between the growing grains. The weld continues to cool and contract. That contraction creates strain across these weak liquid films. If the strain exceeds the ability of the remaining liquid film to accommodate it, the film ruptures and a centerline crack forms. Weld geometry is also important. A deep, narrow weld bead creates conditions that can increase the risk of centerline cracking. The presentation specifically highlights the depth-to-width ratio as an important consideration. Surface contamination can also contribute. Scale, rust, oil and grease should never be treated as harmless contamination. They can introduce elements or gases that adversely affect weld metal chemistry. Low melting point metal contamination, including copper, tin, lead or zinc, can also create serious problems. From an inspection perspective, this reinforces an important principle: inspection begins before welding. Joint preparation and cleanliness must be verified before the first arc is established. Now we move to another major crack mechanism: hydrogen-induced cracking. Hydrogen-induced cracking is one of the most important cracking mechanisms for a welding inspector to understand. It is also known as cold cracking, delayed cracking, underbead cracking, or toe cracking. The word delayed is particularly important. Unlike some welding imperfections that are visible immediately after welding, hydrogen-induced cracking can develop after welding has been completed. It may appear minutes, hours, or even days later. The crack commonly occurs in the grain-coarsened region of the heat-affected zone and may run approximately parallel to the fusion boundary. The slide illustrates two important forms. The first is a root or underbead crack. The second is a toe crack, which initiates around the weld toe where stress concentration is already high. For the inspector, this has a direct practical consequence: inspection timing can be critical. If a project specification or welding procedure requires a delay before final inspection, that requirement exists for a technical reason. The mechanism of hydrogen cracking involves several conditions acting together. Understanding those conditions is the key to both prevention and examination success. We will examine those four factors next. This is one of the most important examination concepts in this section. The presentation identifies four factors required for heat-affected zone hydrogen cracking. The first is hydrogen. The second is stress. The third is temperature. And the fourth is a susceptible microstructure. Hydrogen can enter the welding system through damp consumables, rust, oil, grease, and contaminated surfaces. Stress comes from residual stresses produced by welding, joint restraint and local stress concentrations. Temperature is important because hydrogen behavior changes significantly as the material cools. Finally, the material must have a susceptible microstructure. Hard microstructures in the heat-affected zone can be particularly vulnerable. The presentation gives the examination values associated with these factors: hydrogen above 15 ml per 100 grams, stress above 0.5 times yield stress, temperature below 300 degrees Celsius, and hardness above 400 HV. The key memory technique is to think of the mechanism as a system. If one of the required conditions is effectively controlled or eliminated, the risk of hydrogen cracking can be substantially reduced. This four-factor concept provides the foundation for the prevention measures we will discuss next. The Venn diagram on this slide provides a useful mental model for hydrogen cracking. The three visible environmental and mechanical conditions are low temperature, high stress, and high hydrogen content. The presentation identifies low temperature as below 300 degrees Celsius, high stress as greater than 0.5 times yield stress, and high hydrogen content as greater than 15 ml per 100 grams. The fourth factor is the susceptible microstructure, which is associated with hardenable steels and elevated hardness. The important part of the diagram is the central overlap. Hydrogen cracking requires the relevant conditions to exist together. This gives us a practical way to think about prevention. If we can move the welding condition outside the overlap region, the probability of hydrogen cracking is reduced. For example, preheating changes the thermal history and reduces the tendency to form a hard susceptible microstructure. Reducing diffusible hydrogen addresses the hydrogen component. Reducing restraint or controlling welding sequence can reduce residual stress. The diagram therefore is not simply a theoretical illustration. It gives us a framework for understanding why specific welding controls are required. The next slide converts this model into practical prevention measures. Now we translate the hydrogen cracking mechanism into practical welding controls. The first major control is temperature. Preheating slows the cooling rate. This helps avoid the formation of excessively hard and susceptible microstructures in the heat-affected zone. The specified interpass temperature must also be maintained because each weld pass changes the thermal condition of the joint. Post-heating can be used where specified to encourage hydrogen diffusion away from the weld region. PWHT, when required by the applicable procedure or code, can reduce residual stresses and modify susceptible microstructures. Multi-run welding and temper bead or hot pass techniques can also influence the hardness and thermal history. The second major area is hydrogen control. Low hydrogen consumables must be stored and handled correctly. The joint must be clean and free from rust, moisture, oil and grease. Shielding gas quality and delivery must be controlled. Joint design and welding sequence should also minimize excessive restraint. Finally, weld toes may be blended where specified to reduce sharp stress concentrations. For the inspector, these requirements become inspection checkpoints. Check the consumable condition. Check preheat. Check interpass temperature. Check welding parameters. Check joint cleanliness. And verify that the actual welding operation follows the qualified procedure. Hydrogen cracking prevention is therefore a process control activity, not simply a final inspection activity. Lamellar tearing is a distinctive cracking mechanism associated primarily with rolled steel plate. The most recognizable feature is its stepped or terraced appearance. The mechanism begins with non-metallic inclusions that have become elongated and aligned approximately parallel to the plate surface during rolling. When welding creates contraction strain in the through-thickness direction, stress is transferred across these inclusion regions. If the material does not have sufficient through-thickness ductility, decohesion can occur along the inclusion interfaces. Ductile shear regions then connect the separated areas, producing the characteristic staircase-like crack. This is why lamellar tearing is particularly associated with highly restrained T-joints and fillet-welded configurations. There are two major prevention strategies presented here. The first is the use of suitable Z-grade steel, where through-thickness properties are specified. The second is joint and welding sequence control to reduce through-thickness strain. For examination purposes, remember the combination. Rolled plate, through-thickness strain, non-metallic inclusions, terraced appearance. If you remember those four elements, lamellar tearing becomes much easier to identify. We now move to the second major group, cavities. Cavities are divided into two broad mechanisms, gas cavities and shrinkage cavities. Gas cavities form when gas becomes trapped within the weld during solidification. Shrinkage cavities form because the weld metal contracts as it solidifies. Gas-related imperfections include gas pores, distributed porosity, clustered porosity, linear porosity, elongated cavities, wormholes and surface pores. Shrinkage-related imperfections include crater pipe and other forms of solidification shrinkage. The photograph provides a useful visual reference for gas pores in a weld cross-section. Notice the approximately spherical shape. This shape is an important distinction when comparing gas pores with solid inclusions such as slag. Gas bubbles tend to form rounded cavities because of surface tension. Solid inclusions, on the other hand, tend to have more irregular shapes. As we continue, keep this distinction in mind. Gas gives rounded morphology. Solid inclusions generally give irregular morphology. We will now examine the causes and prevention of gas porosity. This slide reinforces the classification of cavities. The first branch is gas cavities. These occur when gas is trapped during solidification. The second branch is shrinkage cavities, which are associated with volume contraction as the weld solidifies. The gas cavity group includes spherical pores, uniformly distributed porosity, clustered porosity, linear porosity, elongated cavities and wormholes. Wormholes are particularly distinctive because they are elongated tubular cavities and can produce a herringbone-type appearance on radiography. The shrinkage group includes crater pipe and other forms of interdendritic shrinkage. The photograph on the slide shows gas pores in cross-section. Again, look at their geometry. The approximately spherical shape helps distinguish them from slag inclusions. This is a useful example of why a welding inspector should study morphology, not just terminology. When you encounter an indication, its shape can provide a clue about the mechanism that produced it. We will now examine the specific causes and prevention of gas pores. A gas pore is essentially a cavity formed when gas becomes trapped inside the weld metal during solidification. The gas may come from several sources. Moisture in consumables can introduce hydrogen. Oil, grease, and hydrocarbons can produce gases when exposed to welding temperatures. Water or contamination on the joint surface can also introduce hydrogen and other gases. In gas-shielded processes such as MIG, MAG, and TIG, pore shielding can allow atmospheric gases to enter the weld pool. Gas hoses and connections should therefore be checked for leaks. Another potential cause is insufficient deoxidation activity in the electrode, filler metal or parent material. Arc length is also important. An excessively long arc can disturb shielding and increase atmospheric contamination. At first glance, increasing shielding gas flow may seem like an obvious solution. However, excessive flow can create turbulence and actually draw surrounding air into the shielding region. The correct approach is controlled gas flow, not simply maximum gas flow. On radiography, gas porosity generally appears as dark, rounded indications. Wormholes are the special elongated form and may produce the characteristic herringbone appearance. The practical lesson is simple: when you find porosity, don't just record the indication. Investigate the source of the gas. A crater pipe is a shrinkage cavity that forms at the end of a weld run. When welding is stopped, the molten weld pool begins to solidify and contract. If the arc is extinguished suddenly without allowing the crater to fill correctly, the contraction can produce a conical cavity. This is called crater pipe. The important examination distinction is that crater pipe is a shrinkage cavity, not a gas cavity. The prevention method depends on controlled run termination. In TIG welding, for example, a controlled slopeout can gradually reduce current and allow the crater to be filled before the arc completely extinguishes. The welder should not simply stop the arc abruptly while leaving an unfilled crater. The inspector should pay particular attention to weld run termination areas because this is where crater-related imperfections can develop. When examining a weld visually or by NDT, do not concentrate only on the main weld length. Start and stop locations deserve attention as well. The key examination memory point is: crater pipe equals shrinkage cavity at the end of a weld run. We now move to the third major group, solid inclusions. A solid inclusion is a solid foreign substance that becomes trapped within the weld metal. The presentation covers slag inclusions, flux inclusions, oxide inclusions and metallic inclusions, particularly tungsten. The welding process has a major influence on the type of inclusion that can occur. Slag and flux inclusions are associated with welding processes that use flux. Oxide inclusions are associated with oxidation or oxide films entering the weld pool. Tungsten inclusions are particularly associated with TIG welding. Radiographic interpretation is important here because different inclusions can have distinctive appearances. Slag is generally irregular and dark. Tungsten, because of its much higher density compared with steel, can appear as a bright indication on a radiograph. This gives us another useful inspection principle. Always consider the welding process when interpreting an NDT indication. If you know that the weld was produced by TIG, for example, a bright radiographic indication may immediately make tungsten inclusion a consideration. We will now look at the classification and then examine slag and tungsten inclusions in more detail. Slag is the solidified residue associated with flux-containing welding processes such as MMA, SAW, and FCAW. Under normal conditions, slag should remain separate from the molten weld metal and be removed as required between passes. Problems occur when slag becomes trapped. One common cause is inadequate inter-run cleaning. If the previous weld pass is not properly cleaned, the next pass can trap the remaining slag. Incorrect electrode angle can also cause slag to move ahead of the arc and become trapped in the solidifying weld. Irregular weld profiles create additional locations where slag can become mechanically trapped. For the inspector, this highlights the importance of monitoring multipass welding. A weld may look acceptable after one pass, but if inter-run cleaning is inadequate, subsequent passes can introduce internal inclusions. On radiographs, slag commonly appears as an irregular, elongated dark indication. The important practical lesson is that inter-run cleaning is a quality control activity. It is not simply a housekeeping task. Good welding requires the previous layer to provide a clean and suitable surface for the next layer. Now we will examine tungsten inclusions, which have a very different origin and radiographic appearance. Slag is the solidified residue associated with flux-containing welding processes such as MMA, SAW, and FCAW. Under normal conditions, slag should remain separate from the molten weld metal and be removed as required between passes. Problems occur when slag becomes trapped. One common cause is inadequate inter-run cleaning. If the previous weld pass is not properly cleaned, the next pass can trap the remaining slag. Incorrect electrode angle can also cause slag to move ahead of the arc and become trapped in the solidifying weld. Irregular weld profiles create additional locations where slag can become mechanically trapped. For the inspector, this highlights the importance of monitoring multipass welding. A weld may look acceptable after one pass, but if inter-run cleaning is inadequate, subsequent passes can introduce internal inclusions. On radiographs, slag commonly appears as an irregular, elongated dark indication. The important practical lesson is that inter-run cleaning is a quality control activity. It is not simply a housekeeping task. Good welding requires the previous layer to provide a clean and suitable surface for the next layer. Now we will examine tungsten inclusions, which have a very different origin and radiographic appearance. Tungsten inclusions are associated with TIG welding. The most important radiographic characteristic is that tungsten can appear bright or light because tungsten is significantly denser than the surrounding steel weld metal. This is the opposite of the typical dark appearance of slag inclusions. The most common cause is contact between the tungsten electrode and the weld pool. Another cause is exceeding the recommended current capacity for the electrode size or type. Excessive electrode extension can also cause overheating. Poor collet tightening can create instability and overheating. Inadequate shielding can oxidize the tungsten electrode, while cracks or splits in the electrode can also introduce contamination. Good TIG practice therefore includes proper electrode preparation, correct electrode size, appropriate current, correct shielding and adequate post-gas protection. Post-gas flow is particularly important because the tungsten remains hot after the arc stops. The inspector should understand that tungsten inclusion is not simply a welder workmanship issue. It is closely connected to equipment setup and welding parameter control. For examination purposes, remember: TIG plus bright radiographic indication equals possible tungsten inclusion. We now move to the fourth major group, lack of fusion and penetration. This group is particularly important because many of these imperfections are planar. Lack of fusion means that the required metallurgical bond has not been achieved. It can occur at the sidewall, between successive weld runs, or at the root. Incomplete penetration means that the required depth of weld metal has not been achieved. The presentation therefore distinguishes between lack of sidewall fusion, lack of inter-run fusion, lack of root fusion, incomplete penetration and incomplete root penetration. For an inspector, these conditions are particularly significant because planar imperfections can have crack-like geometry. They may therefore be more structurally significant than small rounded pores. Prevention begins with correct joint preparation, correct welding parameters and appropriate welder technique. The inspector should therefore not wait until the final weld to think about fusion. Root gap, root face, bevel condition, cleanliness, welding current, voltage, travel speed and electrode manipulation can all influence the final result. We will now look specifically at the types of lack of fusion. Lack of fusion is the absence of the required union between weld metal and parent metal, or between successive weld layers. There are three major types shown here. The first is lack of sidewall fusion. This occurs when the weld does not properly fuse with one or both sides of the joint preparation. The second is lack of inter-run fusion. This occurs between successive weld beads in a multipass weld. The third is lack of root fusion. This occurs at the root of the weld. The significance comes from the geometry. Lack of fusion is essentially planar, which means that it may have a very small opening but still represent a significant discontinuity. It does not provide the same continuous load-bearing section as properly fused weld metal. It may also be difficult to identify by surface inspection if it is located internally. This is why the inspector needs to understand the relationship between welding technique and likely imperfection location. For example, sidewall fusion problems may indicate inadequate heat reaching the fusion face, while root fusion problems may point toward incorrect root gap, root face, electrode size, or welding technique. Next, we will examine the specific causes and prevention of sidewall lack of fusion. The central principle for preventing sidewall lack of fusion is simple. The arc must provide sufficient heat at the fusion face. If the arc is directed toward the center of the groove instead of the sidewall, the required fusion may not occur. Low heat input can also contribute. Increasing welding current or voltage or reducing travel speed within the qualified procedure range can increase the available heat. Another problem occurs when molten metal floods ahead of the arc. In that situation, the arc may not effectively heat the sidewall. Electrode angle and work position therefore need to be controlled. Oxide or scale on the weld preparation can also act as a barrier. The fusion faces should therefore be properly prepared and cleaned. The slide also highlights inductance in MAG dip transfer welding. Excessive inductance can produce a softer arc and reduce the effectiveness of sidewall penetration. For an inspector, the practical lesson is to identify the underlying cause rather than simply asking for more heat. A qualified WPS defines the permitted welding range. The welder must remain within that range while maintaining correct manipulation. Root fusion is particularly important because the root region of a butt weld can experience significant stress. Several factors influence the ability to achieve proper root fusion. Low heat input is one. An excessive inductance setting in MAG welding can also contribute. Using an MMA electrode that is too large can reduce the current density available at the root. The welding position is important as well. The presentation highlights vertical down welding as having higher deposition but potentially lower penetration compared with vertical up welding. Joint preparation is equally important. A root face that is too large makes it more difficult for the arc to reach the root. A root gap that is too small also restricts access. Incorrect electrode angle or manipulation can direct heat away from the required fusion area. Finally, excessive root misalignment can disturb the joint geometry. This is why fit-up inspection is so important. Before welding begins, the inspector should verify the root opening, root face, alignment and bevel condition against the approved WPS and drawing. If the joint preparation is wrong, the welder may not be able to compensate through technique alone. We now need to clearly distinguish lack of fusion from lack of penetration. Lack of fusion means that the required metallurgical bond has not been established. Lack of penetration means that the weld metal has not filled the required joint depth. Incomplete root penetration is a common example. When examined from the root side, the two root faces may remain visibly unmelted. That is different from lack of root fusion, where the weld metal may have reached the root region but failed to form the required bond. There is another important point on this slide. If a joint is intentionally designed as a partial penetration weld, the portion that is not filled is not automatically an imperfection. The design requirement determines what penetration is required. This is a classic examination trap. Never assume that every joint must have complete penetration. First establish what the drawing and welding procedure require. Then assess the actual condition against that requirement. That is the correct inspection sequence: design requirement first, actual condition second, acceptance decision third. We now move to Group 5, Imperfect Shape and Dimensions. This group covers imperfections associated with the geometry, profile or dimensional condition of the weld and joint. The presentation includes undercut, excess weld metal, excess penetration, overlap, linear misalignment, angular distortion, incompletely filled groove, irregular width, root concavity and burn-through. Many of these imperfections can be identified through visual inspection. However, visual recognition is only the first step. The inspector must also know what characteristic needs to be measured. For undercut, for example, depth and length are important. For misalignment, the offset must be measured. For incomplete filling, the amount of missing weld metal is relevant. For burn-through, the extent of the opening or collapse must be assessed. This group demonstrates why a welding inspector needs suitable measuring tools and gauges. A weld should not be accepted simply because it looks good. Where an acceptance limit is specified, measure the condition and compare the result with the governing requirement. We will begin with undercut, one of the most common imperfections encountered during visual inspection. Undercut is an irregular groove formed at the toe of a weld in the parent metal or previously deposited weld metal. It can be continuous, intermittent or associated with individual weld runs. For examination purposes, remember three characteristics: depth, length, sharpness. These are important because undercut can reduce effective material or weld geometry, while the sharp notch at the weld toe can create a stress concentration. Common causes include excessive welding current, excessive travel speed, excessive or incorrect weaving and incorrect electrode angle. Weld position can also influence the tendency to form undercut. The important inspection point is that undercut should be measured rather than simply described as a minor. The actual depth and length should be compared with the applicable acceptance criteria. There is also an important repair consideration. If undercut is repaired by depositing a very small bead, rapid cooling can produce increased hardness in susceptible materials. This may create a new cracking risk. Therefore, even a small repair should be controlled according to the appropriate welding procedure. For the CSWIP examination, remember: undercut, depth, length and sharpness. This slide covers two related profile conditions: excess weld metal and excess penetration. Excess weld metal refers to excessive weld cap or convexity beyond the specified requirement. A very important examination point is the use of the word reinforcement. Extra weld metal does not automatically reinforce the joint. In fact, excessive cap height can produce a sharp transition at the weld toe and increase stress concentration, particularly under fatigue loading. Therefore, more weld metal is not necessarily better. The second condition is excess penetration. This occurs when the root bead projects beyond the specified profile. Maintaining a controlled root bead is particularly challenging in pipe welding where the reverse side may be inaccessible. The weld profile depends on several factors, including root gap, root face, heat input and welder manipulation. The inspector should compare the actual profile with the specified dimensional limits. Do not make an accept or reject decision based simply on whether the weld looks strong. A professional inspector evaluates geometry against the applicable requirement. Overlap occurs when weld metal flows onto the parent material but fails to fuse properly with it. This makes overlap fundamentally different from simply having a large weld profile. The metal has flowed beyond the intended weld boundary, but the required metallurgical bond has not been established. Common causes include poor electrode manipulation, excessive heat input, low travel speed and an overly fluid weld pool. Welding position can also influence the condition. The presentation highlights the possibility of undercut and overlap occurring together in horizontal vertical fillet welding. When the weld pool becomes excessively fluid, gravity can cause the weld profile to collapse. This can produce undercut at one location and overlap at another. This combined condition is referred to in the presentation as sagging. From an engineering perspective, overlap creates an unfavorable toe geometry and can become a potential fatigue crack initiation site. So when examining a fillet weld, don't focus only on leg length or throat. Look carefully at the transition between weld metal and parent material. The toe should form an appropriate, properly fused transition. This slide addresses two-dimensional conditions, linear misalignment, commonly called high-low, and angular distortion. Linear misalignment occurs when two surfaces are parallel but offset from one another. You may hear it described as mismatch or offset. It is normally measured in millimeters. Angular distortion is different because the surfaces are no longer at the intended angle. It is measured by assessing the angular deviation over a specified distance. An important point from the presentation is that linear misalignment is fundamentally a joint preparation or fabrication issue rather than a weld metal imperfection. Nevertheless, it is assessed during welding inspection because it can influence structural behavior and acceptance. Even a relatively small high-low can introduce local stress and bending effects. The correct inspection method is measurement. Use an appropriate bridge gauge, ruler, or other calibrated measuring device and record the actual offset. For angular distortion, use a straightedge and measure the deviation over the specified distance. Never rely on visual estimation when the specification gives a numerical acceptance limit. This slide covers three additional profile conditions. The first is an incompletely filled groove. This occurs when insufficient filler metal has been deposited to fill the specified groove profile. The important distinction from undercut is the engineering effect. Incomplete filling reduces the cross-sectional area and therefore can reduce load carrying capacity. Undercut, by comparison, is particularly significant because it creates a sharp notch and stress concentration. The second condition is irregular width. This means the weld width changes excessively along its length. The significance depends on the application. In some materials or services, variations in weld width can influence heat-affected zone characteristics or corrosion performance. The third condition is root concavity, also called suckback. This is a depression in the root profile caused by shrinkage. In TIG pipe welding, excessive backing gas pressure can contribute to suckback by pushing the molten root inward. The prevention principle is to maintain the correct welding energy, fit up and backing gas conditions according to the qualified procedure. These three conditions demonstrate why weld profile must be evaluated in relation to both geometry and service requirements. Burn-through is one of the most obvious welding imperfections. It occurs when the molten weld pool becomes unstable and collapses completely, leaving a hole or severe opening through the material. It is particularly common during root welding on thin material or where the root gap is excessive. Several factors can contribute. Insufficient travel speed allows excessive heat to accumulate. Excessive welding current produces excessive heat input. Poor welder control can also contribute. Excessive grinding of the root face can leave insufficient material to support the molten pool. And an excessive root gap makes collapse much more likely. The prevention strategy therefore begins with correct fit-up and controlled heat input. For the inspector, burn-through is not simply a cosmetic problem. A hole represents a significant loss of material continuity. Repair may therefore require careful excavation and controlled welding in accordance with the approved repair procedure. The key practical lesson is that correct root preparation and welding parameters are the most effective way to prevent burn-through. We now move to Group 6, miscellaneous imperfections. This group includes several conditions that do not fit conveniently into the previous classifications. These include stray arcs or arc strikes, spatter, torn surfaces, grinding marks, chipping marks, underflushing, misalignment of opposite runs and temper color. Some may initially appear cosmetic. However, their significance depends on the material, service conditions and governing specification. For example, an arc strike can create a local heat-affected zone and potentially introduce cracking. Excessive grinding can reduce material thickness. A torn surface caused by removal of a temporary attachment can require repair and examination. Temper color on stainless steel can provide information about shielding and oxidation during welding. So the important inspection principle remains the same. Do not judge an imperfection solely by appearance. Identify what it is, determine how it was produced, understand its potential effect, and compare it with the applicable requirement. We will begin with stray arcs or arc strikes. A stray arc, commonly called an arc strike, occurs when the welding arc is unintentionally established outside the intended weld area. This produces a small localized melted region on the parent material. The concern is not simply the mark itself. An arc strike creates a local thermal cycle and can produce a hard heat-affected zone, particularly in susceptible materials. That region may contain microcracks. Under fatigue or dynamic loading, those cracks can become significant. The presentation therefore recommends controlled removal by grinding rather than simply welding over the damaged area. The reason is straightforward. Welding over the arc strike introduces additional heat, creates another heat-affected zone and can complicate the repair. After grinding, suitable surface examination such as magnetic particle inspection or dye-penetrant examination may be required to confirm that cracking has not remained. Prevention involves good equipment control. The electrode holder or torch should be properly insulated, the current return connection should be secure, and the welding equipment should be maintained. A good welding inspector should therefore treat an arc strike as more than a cosmetic mark. It is evidence of localized uncontrolled welding and may require further evaluation. Spatter consists of small droplets of molten metal that are expelled from the weld pool and adhere to nearby surfaces. The presentation classifies spatter primarily as a cosmetic imperfection. However, excessive spatter is also a useful indication that welding conditions may not be properly controlled. High arc current, excessive arc length, magnetic arc blow and incorrect electrical settings can contribute. Damp electrodes can also increase problems. Shielding gas composition influences spatter, particularly in MAG welding. A higher argon content can reduce spatter compared with pure carbon dioxide, although the gas mixture must still provide the required penetration and fusion characteristics. This illustrates an important engineering principle: changing one welding parameter can create a different problem. Reducing spatter is not useful if the change causes lack of penetration. In pressure vessel and pipeline work, adhering spatter may need to be removed before final inspection because it can trap moisture, interfere with surface examination or violate project requirements. Therefore, the inspector should not simply say, "Remove spatter." Where excessive spatter is observed, investigate the welding conditions that produced it. This slide covers several miscellaneous surface conditions. A torn surface can occur when temporary welded attachments are removed by excessive force, such as hammering or bending. The removal process can tear material from the parent surface. The damaged area should be properly dressed and examined as required. If repair welding is necessary, it must be performed using an approved procedure. Grinding marks can also become an issue. Excessive grinding may remove material and reduce the component below the required thickness. This condition is referred to as underflushing. Chipping marks can create local notches and may have a similar effect to other localized surface damage. Misalignment of opposite runs refers to the difference between the centerline positions of weld runs made from opposite sides of a joint. Finally, temper color is particularly relevant to stainless steel TIG welding. The visible oxide color provides information about the degree of oxidation and therefore the effectiveness of shielding. The practical lesson is that surface preparation itself can introduce imperfections. Grinding and cleaning are essential inspection activities, but they must be controlled. A good inspector therefore examines not only the weld but also the condition of the surrounding parent material. Standards. Finding an imperfection does not automatically mean rejecting the weld. The inspector must determine whether the imperfection exceeds the acceptance limit specified for the particular application. Acceptance requirements are normally contained within the applicable construction code, specification, or contract documentation. Different standards can establish different limits for the same type of imperfection. This means that the inspector must always know which standard applies to the job. The presentation also introduces two broad repair approaches. A surface imperfection may sometimes be removed by superficial dressing or blending, provided the remaining material thickness remains within the permitted requirements. If the imperfection is deeper, excavation followed by weld repair may be required. But repair welding must be controlled. An approved repair procedure must be used, and the repaired region must receive the required inspection. The most important principle is this. Identify the imperfection first. Identify the governing acceptance standard second. Then make the acceptance decision. Never reject or accept based purely on personal experience. The contract and applicable standard control the decision. His slide brings the acceptance principles together. First, cracks are normally rejected under standard weld acceptance requirements. The presentation also notes that exceptional cases may require specialist fracture mechanics assessment. That is not a routine welding inspector acceptance decision. Second, and extremely importantly, the contract-specified acceptance standard must always be used. Different standards and different quality levels can have different acceptance limits. Using the wrong standard can therefore produce an incorrect accept or reject decision. Third, consider the repair hierarchy. If a surface imperfection can be removed through controlled grinding or blending without reducing the remaining thickness below the required minimum, superficial dressing may be sufficient. If the imperfection is too deep, it may need to be excavated and repaired by welding. Any weld repair must follow an approved procedure. The repaired area must then receive the inspection required by the applicable specification. So the professional approach is: identify, measure, compare, decide, repair if required, re-inspect. That sequence is fundamental to welding quality control. And remember, the inspector does not invent acceptance limits. The applicable standard and contract requirements determine them. This slide is designed as a rapid revision tool. The first group is cracks. On radiography, cracks are generally narrow, dark and irregular or jagged indications. The second group is cavities. Gas pores are generally dark and rounded, while wormholes can produce elongated or herringbone-type patterns. The third group is solid inclusions. Slag is normally dark, irregular and elongated, while tungsten can appear as a bright indication because of its high density. The fourth group is lack of fusion and penetration. These can produce dark, sharp-edged linear indications and may follow the fusion boundary or weld direction. The fifth group is imperfect shape. Examples include undercut and burn-through, which can have distinctive surface or radiographic characteristics. Finally, miscellaneous imperfections include conditions such as arc strikes, spatter, and temper color. For examination preparation, a useful exercise is to cover the radiographic appearance information and test yourself. Ask: what would this imperfection look like on an X-ray? Then ask a second question: why does it look that way? That second question is important because understanding the mechanism makes memorization much easier. Remember especially the distinction between dark rounded pores, dark irregular slag, bright tungsten, and narrow crack-like indications. This is your final examination-focused revision slide for Section 3. There are 15 key points that you should be able to recall confidently. First, remember that an imperfection is not automatically a defect. Second, remember the 6 groups defined by BSEN ISO 6520-1. Third, solidification cracks occur in the weld metal and commonly follow the centerline. Fourth, hydrogen-induced cracking requires the combination of hydrogen, stress, temperature and susceptible microstructure described in this section. Fifth, lamellar tearing is associated with rolled steel plate, through thickness strain and a characteristic stepped appearance. Sixth, gas pores are generally spherical, while slag inclusions are irregular. Seventh, tungsten inclusions can appear bright or white on radiography. Eighth, lack of fusion is planar and therefore potentially serious. Ninth, understand the difference between incomplete root penetration and lack of root fusion. 10th, remember the 3 characteristics used to assess undercut, depth, length and sharpness. 11th, don't assume that excess weld metal strengthens a joint. 12th, arc strikes should generally be removed by controlled grinding rather than simply welding over them. 13th, excessive spatter is a warning that welding conditions may not be optimal. 14th, understand the normal treatment of cracks under acceptance standards. And 15th, always use the acceptance standard specified for the actual contract or application. Don't simply memorize these 15 points. Try explaining each one without looking at your notes. If you can explain the mechanism, appearance, cause and inspection significance, you have much stronger knowledge than simple memorization. That brings us to the end of Section 3, Welding Imperfections and Materials Inspection. We have covered all 6 major groups of welding imperfections identified in BSEN ISO 6520-1. We examined the mechanisms, causes, and prevention of the principal imperfections. We also considered their visual and radiographic characteristics, because inspection is not simply about knowing terminology. A competent inspector must be able to recognize what an indication represents. We then looked at acceptance standards and repair principles. For your examination preparation, there are 4 activities I strongly recommend. First, revise the 15 key examination points from the previous slide. Second, study the applicable acceptance levels of BSEN ISO 5817 and understand that the actual project specification determines which acceptance requirements apply. Third, practice identifying imperfections from radiographic images. And fourth, repeatedly review the 4 factors associated with hydrogen-induced cracking and the corresponding prevention strategies. The key standards identified in this presentation are BSEN ISO 6520-1, BSEN ISO 5817, and BS 7910, together with the TWIWS 5 course material. As you prepare for the CSWIP 3.1 examination, try to approach every question from the perspective of a welding inspector. Ask yourself, what is the imperfection? How did it form? How would I detect or measure it? What is its significance? And finally, which acceptance standard applies? That is the professional inspection mindset. Thank you for completing Section 3. And good luck with your CSWIP 3.1 examination.